The steamship Titanic was launched in May 1911. On the 10th of April 1912, she sailed from Southampton on her maiden voyage, bound for America with 2,200 people on board. She was 270 metres long and built entirely of steel, the biggest steel ship ever built. Some people were amazed that a steel ship would float at all. How do you think 45,000 tons of steel can float? She was the grandest passenger liner the world had ever seen, and Captain Edward Smith was proud of his ship. They also thought the Titanic was the safest ship ever built. They called her the Unsinkable. 3 days later was Sunday. She was halfway across the Atlantic. In the evening, the passengers were wining and dining. On the 4 passenger decks, there was every sort of luxury, from a swimming pool to a Turkish bath. Steaming along at 22 knots, they saw ahead what looked like just a little lump of ice. The time was 11:45. It felt like just a little bump, not even enough to spill the drinks on board. The passengers weren't worried. They didn't realise that the ship had been holed below the waterline. Icebergs are much more dangerous than they look. Let's see the collision again. All you can see is the tip of the iceberg. 9/10 of it is hidden under water, and there are often jagged bits sticking out below the surface. So when the Titanic hit the iceberg, the collision was underwater. Captain Smith ordered the passengers into the lifeboats, but there weren't enough lifeboats for everyone on board. At 2:20 a.m., the Titanic went down. The unthinkable had happened. The unsinkable had sunk. "700 people were rescued, but 1,500 were drowned." Why do icebergs float mostly underwater? How do ships made from steel manage to float at all? And why did the Titanic sink when the water ran in? Some objects sink in water, but others float. What decides whether something sinks or floats? Tomatoes sink to the bottom, but bananas float up to the surface. Can you explain why? And if you push down something that floats, like a football, what happens when you let go? What pushes it up again? Hippos are massive animals. So are manatees, or sea cows. Even the calf is much bigger than a person. Nearly a ton, a good mass for a manatee. But in the water, all its weight seems to disappear. It floats about like an astronaut. What's lifting it up? The word hippopotamus means river horse. Why is it so light on its feet? And what about you? Why do you float like an iceberg with your head sticking out of the water? Where's your weight gone? If you were lowered slowly into a pool, what would happen to your weight? These scientists are studying the weights of objects hanging in water. When a brick is lowered into water, its mass stays the same, but its weight gets much less. So what's pushing it up? A tin of beans weighs 2.5 newtons in air, but much less in water. There's an upthrust of more than 2 newtons. With an apple, the effect is even more dramatic. Its weight drops right down to 0. Any object will float in water if the upthrust is as big as its weight. How about you? If you were lowered into water, how much upthrust could you expect? If you went all the way down, would the upthrust equal your weight? Lowering things into water solved a royal problem for a Greek scientist called Archimedes. The king had given the crown maker a block of pure gold for a new crown. But when it came back, the king was suspicious. Had the crown maker pinched some of the gold and mixed in some cheaper metal? Archimedes weighed the crown. The mass was right. What about the volume? Cheaper metals are lighter than gold for their size, so if it wasn't pure gold, the volume would be greater. Before he could face the king in the morning, Archimedes wanted a bath. He was still worrying about the volume of the crown as he lowered himself into the warm water. And then he had a brilliant idea.
Eureka!
When he'd lowered his body into the bath, it had pushed some water out. If he lowered the crown into a bucket, it must displace its own volume of water. The volume was too big. There was some cheap metal in it. The king was not pleased. What the crown maker hadn't realised was that a given mass of gold has a particular volume. You can't escape it. The king got his gold back, and Archimedes lived happily ever after, thanks to his idea of displacement. You can use displacement to measure the volume of an awkward-shaped object like your hand. As long as the inner container is full to start with, the volume of your hand must be exactly equal to the volume of water displaced. Could you do that with a whole person? What precautions would you have to take to make sure it's a fair test? And how would you measure the volume of water? When you know the volume and the mass of something, you can work out its density. The density of any material is the mass of 1 cubic centimetre. So the density of plasticine is 3.0 grams per cubic centimetre. Different materials have different densities. Most metals are dense, and brass has a density of 8.4 grams per cubic centimetre. The density of water is 1 gram per cubic centimetre, and anything denser will sink. How can you predict what will float? Wood has a low density, so you'd expect wooden boats to float. But what about big steel ships? Why doesn't the steel sink? Do you think the shape of the object matters? Can you make a boat out of plasticine? Plasticine has a density of 3 grams per cubic centimetre. So you'd expect lumps to sink in water, but if it's the right shape, it floats. That's because it displaces more water. Take a wide boat with a loose bottom and push it down, and it displaces a lot of water. Why doesn't the bottom fall off? It still doesn't fall off with a heavy weight on because there's a lot of upthrust. As long as enough water is displaced, there's enough upthrust to carry tons of coal. But what happens if the boat fills up with water? What happens to the upthrust? So now, can you see what happened to the Titanic? They thought she was unsinkable because she had steel bulkheads dividing her into separate compartments. If one compartment filled with water, it wouldn't matter. But the iceberg probably ripped a hole in 4 of them. Some solids are denser than others. What about liquids? Different liquids also have different densities. That means that a liquid with a low density will float on top of a liquid with a higher density. One liquid that is less dense than water is alcohol. What if you drop things in? Remember, in water, bananas float, but tomatoes sink. What will happen in a liquid that gets denser as you go down? Why do you think the 2 bits of banana float at different levels? Why do you think they float in layers? Submarines need to be able to float and sink. To do that, they behave like whales. Before they dive, whales blow. They have to breathe out to get rid of the air and increase their density. So do submarines. Inside, submarines have big tanks they can fill with air or water. Fill them with water and the submarine sinks. Can you work out why? And how do you think it comes up again? Divers also need to change their density. There's a lot of air trapped in the suits. Why do you think they need heavy belts? One thing that has a much lower density than water is air. Bubbles of air rush upwards. How could you use the low density of air to raise this valuable old wreck? So if you were a salvage expert and you found an aircraft at the bottom of a lake, how many ways could you think of to raise it to the surface? What difference does being underwater make to the weight? And if you'd found the steamship Titanic at the bottom of the Atlantic Ocean, how would you go about trying to lift her? And what other problems might there be? Some structures are stronger than others. What use is this to stunt drivers? What strong structures do they use for protection? And what What is it that makes things collapse? Things collapse when they can't take the force. What different kinds of force can you think of? There are 4 main kinds of force: push, pull, bend, and twist. Push, pull, bend, twist. With special lighting, you can see what happens when the same forces are applied to a piece of jelly. The coloured bands show the strain in the jelly. The strain doesn't happen only where the force is applied, it goes right through the jelly. Bending causes strain right through the jelly too, and twisting is too much for it. What sort of forces are these? What sort of forces do bridges have to take? And how do you measure them? You can measure the weight of a truck with a weighbridge. Why do you think some bridges have weight limits on them? And where else have you seen weight limits? If you were fishing, you wouldn't want your fishing line to break. How much mass do you think this fishing line will take? How would you measure the pulling force needed to break something? Like a rubber band, for example. Or a carrier bag. If you want to find out what pushing force is needed to make something collapse, you can use a pushing force meter. At what moment do you have to read the scale? You can calibrate any force meter by using standard Newton weights. Suppose you were making clothes pegs. How would you test them? You'd want to make sure they wouldn't break when you pushed the ends apart and that the clothes wouldn't fall out by mistake. Do you think this is a fair test? How else would you do it? These scientists are making bridges out of spaghetti and other sorts of pasta. If you had to do that, how would you test the strength of the pasta? What forces are going to be put on it? Do you think this is a good way of measuring what pushing force is needed to break macaroni? Macaroni is strong because tubes are strong shapes. Tubes don't break easily. But although tubes are strong, they're even stronger with triangles inside. Triangles are strong shapes. And because they're strong shapes, you can build lots of different things from triangles. What else can you think of that's made of triangles? And where else can you find triangles used to hold things up? How would you test the strength of different shapes? These scientists found that pentagons are puny and that squares are easily squashed. But triangles are tough. Why do you think they can take so much force before they collapse? These scientists wanted to design a bridge. The bridge had to go across this gap and support the flexible track so that an 800-gram car would run across and get to the other side. And the bridge had to be built from the least possible amount of spaghetti. First, they tested the spaghetti with various forces. It can take a small bending force, but a much bigger pulling force. A small pushing force on a long piece of spaghetti makes it bend or buckle. But a piece that's not long enough to bend takes a big pushing force before it breaks. Most of the bridges were made by gluing short pieces of spaghetti into triangle shapes. Suppose you wanted to design a bridge to take a road over a river. Why do you think it might be a good idea to start with models? What would model testing save in terms of time, energy, and money? Which of these designs do you think is best? Testing model structures is cheap and useful, but sometimes you have to do a full-scale test on the real thing. Radioactive fuel elements are transported in these white flasks. The radioactive rods go in a steel box which fits inside the flask. Each flask costs £250,000 and has a mass of 50 tons. The steel walls are 35 centimetres thick and the lid is held down by 16 huge bolts. Are the flasks strong enough? Suppose one was involved in a train crash. Would it break open and spill dangerous radioactive material? To find out, they derailed a yellow test flask and drove a train into it at 100 miles an hour. The train suffered a bit, but the flask didn't break open. Building materials like stone, brick and concrete are very strong against pushing forces, but weak if they're pulled. That's why these blocks break. When he tries to bend them, it's a pulling force that does the damage. Remember the 4 forces? Push, pull, bend, and twist. When a bar bends, the top edge is squashed by a pushing force, but the bottom is pulled. So where do you think it'll break if you try and bend it? So, bending forces can break stone. When bridges were made from stone, the engineers had to avoid bending forces. Can you work out why they made arches? In an arch, all the forces are pushing forces, and stone is very strong against pushing forces. If you look at old buildings, you often find that the only things left standing are the arches. Like tubes and triangles, arches are strong shapes. Why do you think this groin-vaulted roof has survived so long? This bridge was cast in iron and put up in 1779. In this old barn, the roof is held up by timbers. You can't easily bend timber into arches, but they used triangles to make arch-like shapes. How do you think they joined the timbers together? What sort of joint do you think might be strongest? A mitre joint? A mortise and tenon joint? Or a dovetail? Why do you think things often break at joins? And why do you think joins are important to the strength of structures? Arches are strong shapes, and arched ribs are what we use to protect our heart and lungs. But the brain is protected by a dome. Why do you think domes are strong shapes? Eggshell is weak, easy to break. What will happen to the eggs in this box? Only one gets broken. How strong are eggs? An egg is like 2 domes joined together. Do you think it will take more pushing force on the side or on the end? And which end do you think is stronger? Why do you think it's so hard to break an egg by squeezing it? Remember, eggshell is weak. Why are eggs so strong? Some animals live inside domes for protection. They don't need any bones inside. These animals have skeletons inside to hold them up, but animals like crabs have an exoskeleton. They have hard domes for protection. There are no bones inside, but the domes go all the way around to keep them safe. Many seashore animals have exoskeletons. This is a mussel. Cut it open and you can see that inside the dome it's soft and unprotected. What other animals can you think of with exoskeletons? And when might people use the same idea? You need protection for lots of different sports. How many can you think of? So, what makes a helmet strong? What is it about the shape of a car that gives it strength? Why did the driver wear arches round her neck? And how else can we use strong shapes to protect things from damage? There's always a danger of fire, particularly when people are careless.
Upstairs, thanks. What's the water? Come in. Look upstairs.
The fire brigade use water for most fires in houses, but different methods can be better for different kinds of fires.
Hold the horn there.
Extinguishers filled with carbon dioxide are useful indoors. Why do you think they aren't very effective outside? For a wood fire, the best thing is water.
Right, work all round it, in between the wood.
For a fire in a chip pan, use a damp tea towel.
Drape it over. Out straight away. Remember, once it's out, don't pick the pan up and take it away. Let the pan cool.
For an oil fire, what you must never use is water.
That's why you should never use water on an oil fire. Flares up like that. Not always flares up, but it can spill over the side.
The best way to put out an oil fire is with an extinguisher of dry powder.
That's it. As quick as that.
To find out about fire, you need a scientific eye. Why do things burn? Before any flame will burn, it needs three things. What are they? The three things needed for a fire are often represented as a fire triangle. A flame is a chemical reaction. It needs fuel, oxygen and heat. Fuel to burn, oxygen to react with it, and heat to start the reaction and to keep it going. What will happen if you cut off the fuel? What if you cut off the oxygen? Why doesn't the paper catch fire? There's water inside it. The water takes the heat away, and without the heat, the paper won't burn. Things we can burn safely to get energy we call fuels. Candle wax and camping gas and wood are all fuels. How many useful fuels can you think of? There are 6 different fuels being used in this village. Look at what they're being used for. Are there any other fuels that could do the job as well? How do fuels burn? There's a clue here. Some fuels are liquids. But what actually burns is not the liquid, but the gas or vapour that comes off it. Here are 3 fuels: methylated spirits or meths, petrol and paraffin. Paraffin is a useful fuel, but it doesn't catch fire easily. Let's find out why. Look carefully at this petrol flame. Notice where it comes from. Does the petrol burn from the bottom of the liquid or all the way through? No, the flame starts well above the surface. Here's some warm fuel in a beaker. None is tipping out, but the shadow shows that something is pouring from the spout. There's fuel vapour above the surface. Vapour is what's pouring out. Could it be the vapour that burns? Warm fuel light the vapour above the gauze. So it is the vapour that burns. The flame never gets near the liquid at all. Some fuels give off vapour more easily than others. So now can you think why the paraffin on the right did not catch fire? Let's see how easily different fuels catch fire or ignite. Gases ignite very easily. It only takes a spark or a match. This welding torch uses acetylene gas. The gas burns easily because the torch mixes it with oxygen. Watch what happens in slow motion when a cylinder of fuel explodes near a flame. First, vapour mixes with air, then it ignites. It's because gas ignites so easily that gas explosions are so dangerous. Gas explosions can bring whole buildings to the ground. So, what should you do if you smell a gas leak? Space rockets use gas fuels. And they have to carry both the fuel and the oxygen with them. There's no oxygen in space. If you want a solid to burn as fiercely as this, you have to pack oxygen in with it. The sparks are little bits of burning iron. They burn because there's oxygen trapped chemically in the sparkler. All fireworks have oxygen trapped chemically in them. That's why the little bits of solid burn so brightly. This slow-burning fuse has chemically trapped oxygen in it. What do you think will happen when the flame gets down to the water level? What other solids will burn easily? Not fiberglass, that's why it's used for insulation. Nor pots made from clay. Lumps of coal don't catch easily either. Even wood won't light in big pieces. But smaller pieces of the same wood will ignite. And shavings catch fire easily. Why does this happen? Remember, lumps of coal won't ignite, but coal dust will burn easily if you blow it into a flame. So will aluminium powder. Solids will burn if they're in small enough pieces and if they're thoroughly mixed with oxygen. Powders like flour and icing sugar are just the same. Corn flour won't burn in a heap. But see what happens when it's thoroughly mixed with oxygen. Flour and even custard powder can make devastating explosions. This factory in Banbury was blown apart by one. That's why scientists investigate dust explosions to try and prevent them. Someone once blew up a piano as part of an act. That was 9 ounces of explosive powder, but for extra drama they put in some flour. Look what happened with only half the explosive plus flour. What about the colour of flames? A meth flame is blue. A petrol flame is yellow. Can you guess which might be the hotter and the more dangerous? A Bunsen flame is yellow when the air hole is shut, but it changes if you open the air hole. Can you explain why the flame goes blue? Candle flames are yellow and very dirty. Might this make any difference to how hot and how dangerous they are? On the 14th of February 1981, at this disco in Dublin, there was a terrible fire in the early hours of the morning. 50 teenagers died, and afterwards the whole building was a wreck. What the scientists wanted to find out was how the fire had spread so quickly. First, they looked at the materials in the disco. How easily would they ignite? They found that the seats could not be ignited with a lighted match, unless the seat cover was already damaged. So the fire couldn't have spread along the seats. But they wondered about the carpet tiles that had been on the walls. They built a replica of part of the disco inside a huge building and started a little fire on a seat at the back. Sure enough, the fire burned quickly up the wall to the ceiling, and then it spread, not over the seats, but across the ceiling. Fierce heat from the yellow flames above quickly set fire to more rows of seats. Watch the ashtray on the table on the left. Within 90 seconds, the room was a raging inferno. What should you do if you spot even a little fire?